All right. Morning. Thank you guys for being here. I just wanted to take today to just kind of keep doing what we've been doing, work through a couple things, and I wanted to start with what we ended with last time because we really didn't get a chance to practice too much of it, and that's circle equations. Okay. Knowing that our setup always has a center and a radius. And that center is going to be at some point, hk, and the radius is r. We have a really nice setup for the equation no matter what. X minus h squared plus y minus k squared, and that's equal to r squared. Or we'll actually go through the process of like dropping in whatever h is and dropping in whatever k is. Careful with those signs there, right? You got some minuses. And then whatever the radius is given, we'll actually just square it and leave it like that. So if the radius was 2, we'd put a 4. If the radius was 10, we'd put a 100, right? If the radius was the square root of 3, we'd put a 3, right? Because you'd square, okay? And just to give you some ones to practice with now, so that you have something to look back at in a couple weeks. Try these 3. Try these 3, right? Okay. So given each center and radius, try it. See if you can write the equation of the circle using that setup. Right. And probably good that if you are going to write this stuff down, that you write down what I gave you first and then the answer. Because this way you know where your answer came from when you look back at it to help you with the final. When it comes to take 1 more minute if you need it. And I'm going to try to teach you 2 things today. And if we can do it, we might be able to get it done by Thursday. We might be done Thursday. We won't have to meet up. I don't know, like 30 more seconds if you need it. I got rid of the beard, mustache, whatever was left of it yesterday. So back to the baby face. Feels good. Since August, crazy. Okay. First one. I would love to hear from you. Somebody that got the first one and they feel pretty good about it. Unmute yourself and tell me what's the right time. Oh, come on. This sucks, just me. Come on, I want to hear from you. Give me something.
X minus 5 squared plus y minus 4 squared equals 9.
Good. Right, 5, 4. So, okay, minus 5, minus 4, and then you take whatever the radius was and you just square it. Good. Okay, second one. Anybody?
X plus 2 squared plus y minus 6 squared equals 16.
Good. All right, had to change the sign, right? It was -2 is the center, so I had to do x plus 2. Always a plus in between, don't forget it. Good, and then x minus 6 squared, and that's equal to 16. Good, so our setup is always the same, right? It kind of looks like that, looks like that. We got an x in the first one and a y in the second one. We just have to make sure we switch the sign of whatever's there. So the center for number 3 with that -3, -7, okay, x plus 3, x plus 7. But if the radius is given as the square root of 10, what number should I put right there? If that's r squared. That's the only kind of tricky part about this one. Right, there's 3 squared. There's 4 squared. I need the square root of 10 squared. So the square root and the square root just cancel each other out, and we just get 10. Right. There you go. There's a question you're definitely going to get right. Now that you've got. Good? Okay, cool. All right. Let's keep rolling. Something that came up that a lot of people were worried about how good they felt about it. So I definitely want to make sure that I touch on that now. Just stay below the glare. Okay. Next idea, switching gears. Composition of functions. Okay, composition of functions. It's just putting a couple things together at the same time, right? If you think of the word composition, like I can think of both kind of an English perspective, right? When you write a composition, you're kind of putting your ideas together into one piece. Sometimes those are different competing ideas or whatever it might be. But I also think of music, right? I think of a composer with music, and if you've ever seen a band director's version of the music, I mean, there's just one line for every single instrument. You could have 10 or 12 or 15 lines, all with different instruments playing at the same time, and the idea is to put all those together. So that's what we're going to do with composition of functions. We're going to have, and we can do as many as we want, but we'll just have 2. There's going to be 2 given functions, and we're going to evaluate them together kind of at the same time. And so I need to show you what that looks like, and also a little bit of notation, because it's going to be a little bit different than maybe you've seen before. Okay, so I'll call it number 1. I'm just going to give us a couple simple functions to kind of start with. So like f of x is equal to, I don't know, I'll make it simple, like x to the 3rd. Nothing crazy. Just plain old x to the 3rd. And then g of x, let's make that pretty nice too. Let's make it like just, I don't know, like x plus 5. Just a nice linear one. Okay. And what they're going to ask us to do is take an x value and drop it into one of those and see what you get. Okay, so let's say x is equal to -2. -2. Okay, and what they're going to do is they're going to tell us which one to plug it into first and see what we get. Okay. And then we're going to take that result and plug it into the other one. So we're going to plug in x into one of the functions, see what we get the y value for, and then take that answer and plug it back in to the other function. Okay, so this is what it kind of looks like. Okay, and it could be in either order. So we're going to actually, I'm going to show us how to do both. Okay, they could say something like f of something, right? But on the inside here would be like g of -2. Or it could be g of f of -2, in which you can want to have a mindset of when you deal with composition is to work from the inside out. Okay, do the innermost parentheses first. Do the innermost parentheses first, and then kind of build your way out from there. And so what this inside says to do is say, take -2 and plug it into G and see what you get. So that's what I'm gonna do. I'm gonna drop -2 in right there and see what happens. Okay, well, -2 right there plus 5 is a positive. Now, f of 3, okay, take 3 and cube it, and you get 27. And that's all they want us to do. They don't want us to stick with the x's and expand and go crazy with binomial expansion or whatever. No, here's an x value, plug it in, see what you get, okay? And the composition could depend on the order. You might not get the same answer by dropping in the x into G and then into F, as you will dropping it into F and then into G. So we want to make sure we kind of work from the inside first and then build our way out. So I'm going to do f of -2 first and see what I get. Okay, so that says take x, make it -2, and plug that -2 into that inside function, that f. Okay, so I'm going to drop -2 in right there and see what I get. -2 cubed is -8. Okay, and then I take -8 and I drop it into G. Okay, -8 plus 5, -3. Okay, so we're obviously going to get, most of the time, different results. Okay, we're going to get different results most of the time. Sometimes it's just coincidence if it works out that way, but the way that I can kind of guarantee that I'm going to get the same result is if f and g were inverses, I'd get that original number back, but that's not going to happen very often. They're going to give us two kind of unique functions and ask us to do some composition. Okay, let me do another one, and I want to throw some new notation at you so you can see what I'm talking about. I'm going to make up some different ones. I don't know, a of x and b of x. Let's go, keep it simple again. I don't know, like 5x squared for a of x. And like -3x plus 1. Like that. Okay. So they're my two functions. And they're going to ask us to do just one, but I wanted to kind of show you in both ways that the order matters, how it's written. Okay. So here's part A, and here's part B, but here's the new composition notation that you might not be familiar with. Okay. And it looks like this. Okay. Parentheses. And in here, I'm going to put a composition. Okay. And the order is going to matter. Okay. A, and then here's the new notation that you haven't seen. It kind of looks like a small zero, a small O, almost like a degree symbol, like 98.6 degrees, right? But it's not quite up here. It's just this small circle, smaller than you would draw a regular O. There's that composition. A of B is a way you can kind of read that. Okay. A of B, and I have to tell you what number to plug in. We'll pick a nice one. How about like 2? Okay. Now this really means, and I hope the first thing that you do is you write it in that exact same order like we have been. A of B of 2. Okay, A of B of 2. You read it the same way out loud. It's going to be written the same way here, but it reminds us when we're writing it with this kind of notation that we're going to do the inside part first and then work our way out. Okay, and since the inside here is B of 2, that's what I want to do first. I want to take 2, drop it into B, see what I get. Okay, and I'll tell you, they're going to write it like this. They're not going to write it like this. It's kind of up to us to make that first leap down to a notation that looks just a little bit easier to deal with, because then it, like having the inside of the parentheses allows me to kind of work in the direction I want to. Okay, B of 2, drop in 2 right there, you get -5. Right, -3 times 2, -6 plus 1. And then take -5 and drop it in up there and see what you get. Okay, A of -5. So it's like this, there's 2 levels. You do one evaluation, see what you get, and you just do another. Okay. So -5 in here, 5 times 25, so 1. Okay. So the order is going to matter for sure. Like if I said B of A of 2, all right, that's B of A of 2. Okay, so you have like this bigger set of parentheses out here and these smaller inside ones. To let you know that you want to be working in a certain order, right? And this is, write it from left to right, just how you read it out loud. Now that I'm evaluating, I'm going to work from the inside and work my way out and see what happens. Okay, so I really want to just kind of look in here and say, right, what's A of 2? Well, A of x is 5x squared, so I drop in 2 squared, that's 4 times 5, so A of 2 is 20. Okay, and the complexity of the functions they're going to give us is going to be pretty low. We're not going to have to do crazy arithmetic. Now I just drop in 20 and see what I get. Negative 60 plus 1, so negative 50. And again, no big surprise to me that I'm getting different results based on that composition. That's it. That's composition of functions. Questions on it before I give you a couple to try? Because I want you to have good practice to look back at. I'll present again. Okay. So there's a couple functions. Evaluate that composition. Okay, so with number 4, I kind of wrote it out nicely for you to start. F of G of 3. And so you just drop in G of 3, all right, see what you get, and then plug that back into F. But then for 5 and 6, there's the notation, and you see the order, right? F of G of negative 2 versus G of F of negative. Okay, so use this as a good guide for something like 5 and 6 to help you figure it out. Okay, take a couple minutes, write these down, right? I'm not giving you homework this week because we're doing as much practice in class. So you want to take this time to get this stuff right now. And then I'll do one more, and we'll be done. Another moment or two if you need it. And you gotta ask questions if you're feeling stuck. Okay, I know that's not always the easiest thing to do, but this is your time. There's like 8 people here. Can't ask questions now. I don't know when that's gonna happen. So plan, the way it looks, is that Monday, Tuesday, when we get back from Thanksgiving break, we'll review, and Wednesday we will take the multiple choice. Okay. It should probably be pretty easy once we get through everything, and once you have the review and you're feeling pretty good about it. Now I'll send out the review well before that. I'll try to put it together for like Friday. So that if you want to start working on it during your time off, so that you're not feeling like you're trying to cram it all in there those last couple days when you'll have other classes that have expectations of you remotely, and I know that the motivation at home is not always easy. So spread out your studying over some time there, and it's going to be a whole lot easier when you get to Wednesday. I think it's going to be easy anyway, but we'll all kind of take it together. There'll be a start and a finish, right? It is a final, so we will have a start time and a finish time. So I'll send that out, and if you have any issues with the timing, you just have to let me know so that we can make alternate arrangements. I would really like to avoid that, though, to preserve the integrity of the test. As easy as it is, I still want to make sure that you're doing your work, not that you would do anything else. But because it's college, I have a couple extra things that I have to make sure I'm doing from my end as required by CU. So there you go. I will put all that out together in a message on Canvas, an announcement, an assignment, really. I'll put it out there so you know what's going on. But there's A, B, and C. Okay, f of g of 3, plug in 3 into g. See what you get. Oh, I got -7. Okay, I'll plug that into f and 77. I don't need to see every little step of arithmetic. That's okay. As long as you can get yourself to that good solution and know what order to plug things in, you're good. Same thing with B and C, but I really wanted to make sure that given this kind of notation, I rewrite it in a way that just looks better for me and my brain, because I can see the inside and work my way out. Right? F of g of -2 is a great way to read that out. It's like this symbol, this little O right here, I just think of the word of, and it reminds me of function notation. Okay, okay, plug in -2 into g, see what you get. Oh, I got 3. Okay, plug 3 into f, what I get? Oh, 27. I hope I'm doing that right. I'm doing all this stuff in my head, so hopefully that worked out okay. And the same thing there, right? G of f of -1, okay, so I just rewrite it like that. G of f of -1. Happen to get -1 back when I plug in -1 into f. It just kind of worked out that way. And then I plug -1 into g, and I get 20. Cool. Sweet. All right, let's do one more thing. Let's do one more idea. Stuff you saw last year, which is why I wanted to end with this one, because I think it'll be familiar. You just probably want a recap to have it written down somewhere. But we're going to keep it short and sweet. Come with me. I will stop sharing. Hopefully you guys are doing okay. Let me know if you have any questions. Okay, cool. Last topic today is something that we decided to skip over in chapter 1 because it was kind of a bigger Algebra 2 idea from last year. So hopefully this rings a lot of bells for you, and once we actually do it, you'll be like, oh yeah, I remember that. Inverses of functions. Okay, last idea of today. I'm hoping that tomorrow will just be, again, like 2 or 3 ideas. Ta-da, we're done. There's the final, and we'll be good to go. We can start trig as soon as we take that final. Okay, so this one is a little bit more of an algorithm. You want to just make sure you know what to do first, what to do second, and then what the notation looks like once you get there. But every function has its inverse, right? But not every inverse of a function is a function, okay? And that's okay. It doesn't have to be. I can still be dealing with, so I didn't say inverse functions of functions, right? I just have inverses of functions. And just a little bit of background, and you won't have to be able to define this or know it for sure right now, but it will come in handy for sure. Once we get to next semester and we get to calc stuff, is knowing whether or not a function's inverse will also be a function, okay? And so the thing that you want to remember about how to deal with inverses will kind of lead you to whether or not you'll know whether the function's inverse will be a function or not. So here's the process. Here's how to do it. Okay. So we're going to be given some function. Given some function. So let's look at like an example over here. Call it example 1. F of x equals, I don't know, 4x plus 3. Let's make it up. When it's written in function notation, it can be a little bit tricky to do it. So what a lot of people recommend is to, instead of using f of x, is to rewrite as y equals instead of f of x equals. So I would just say, you know what, I'm going to drop the function notation part of this and just use y instead, just because it's just simpler, because it's just one variable rather than a function of another. Good place to start, okay? And I mean, I'll ask you, I don't know if you guys remember, but do you know what to do right now, like to get ourselves from a function to its inverse? Because I just want to kind of make that switch, right? I want to go from addition to subtraction, or from multiplication to division. I just want to do the opposite, but I want to figure out an easy way to write that algebraically. Do you remember what this next step is? What we switch? We switch x and y. We take every x and every y, and we switch them. Okay, and that's what makes the inverse part. Like, this is still the same function. This x equals 4y plus 3. That's now the start of the inverse. Okay, there's my function. There's the inverse. Okay, where x and y are completely switched. Okay. We just don't usually leave it like that. We want to try to isolate y so we can write it as a function. Okay. So after I switch x and y, I just try to isolate y. And we're going to keep things rather simple. There's only going to be one x in the whole problem, and of course just one y in the whole problem because it's just a function. So when you make the switch, you really only have to solve for a single y. You won't have to do too much maneuver there. But that's all I want to do, is I want to get this y by itself, and so I'm just solving for that. So I just start kind of moving stuff away. Whatever I need to do to start solving for a variable. And usually a good way to do that is to undo order of operations going backwards. Right? Take care of any addition subtraction first. So like subtract 3 on both sides. Okay? Addition subtraction done. Now divide by 4. And you can just make one big fraction on the left-hand side, or you can individually divide each piece by 4. Either one's fine. Just know that they mean the same thing, right? I like this one personally because sometimes some of the things could simplify and some might not. In this case, there's really not much I can do here. But I'm gonna write it as like 1/4 x, coefficient of x, minus 3/4. And that's equal to y. There it is, isolated y. Now I just use inverse function notation. Use inverse notation. Okay, and what I mean by that is, well, if this function from the beginning was f of x, then this right here is the inverse of f of x. And we write it like this. Between the f and the x. And I called it f because that's what it started. If this was g, then this would be g. If this is h, then this is h, right? Between the f and the x, I put a little notation spot up in what would be the exponent area. Obviously, it's not an exponent. That's just notation of a -1, -1 in that spot. And I read this out loud one of two ways. The inverse of f of x or f inverse of x. Either one's fine. What is it? Oh, it's just all that there on the other side. I just like to make the switch and put the good stuff, the inverse stuff on the left and then the actual equation over there. Okay. And that's it. That's how we're going to do it. Okay. Every time we want to find inverses, rewrite it as y equals, switch x and y, solve for y. And then whatever you get, just use that nice inverse notation where you put the little -1 after the name of the function but before the input, whatever that x. Okay. And so back a little bit, now that we have a little background knowledge, how can I tell if my function's inverse will also be a function? Well, remember your test for functions visually. All right, if I want to know if my my graph is a function, I don't know, making it up. There's a polynomial. If I want to know if this graph is a function, I'll just check the vertical line test, right? I'll pass a vertical line through it and make sure it only hits it at most one time in each of those spots, okay? Great. It either is or it isn't. Whatever we got, right? But if I want to test for an inverse function, if I want to look at a graph and know whether or not that graph not is a function, but whether its inverse will be a function, well, switch x and y. Right? That's what makes it an inverse, right? Is to take x and y and basically switch them. So that's what I'm going to do here. Instead of taking a vertical line and passing it through all of the x values, I'm going to take a horizontal line and pass it through all the y values. I'm going to do the horizontal line test and check to see what happens. Okay, it either passes or it doesn't. Whatever it is fine. Okay, this is just notation, right? That just tells me this is the inverse of what you had. Okay, but if I'd like to know whether it's a function or not, vertical line test. If I want to know if its inverse will be a function, so not the graph of the inverse, but here's the graph of the function. Will its inverse be a function when I make all that switch? I take a horizontal line and I pass it through. So this one would fail, right? Draw a horizontal line through this graph. I mean, there's one of many spots right there where it would hit it more than once, okay? So this graph is not going to have an inverse whose graph is a function, okay? So there you go, okay? If it passes both, it's pretty unique, okay? If a graph passes both the vertical line test and the horizontal line test, okay? Meaning for every x value, there's only a single y value. So for every one x, there's only one y that goes with it, right? Stop at any x, there's only one point that I'm gonna run into. And vice versa, right? For every y value that I run into, I'm only ever going to find one x that makes that y value happen, right? So for every one x, there's a y, and for every one y, there's an x. Okay, if it does both, it's unique and it's really nice. We really, really like these. Okay, do you know, have you ever heard of that? Where it passes both the horizontal line test and the vertical line test? What kind of functions these are? They're called one-to-one functions. For every one x, there's only one y, and for every one y, there's only one x, which means it had to have passed both the vertical and the horizontal line test, okay? One-to-one functions we really like, because then I know that graph of that, whatever that relationship is a function, and its inverse will also be a function, and we really, really like it, right? So if the test just mentions that it's a one-to-one function, all you really just have to be happy about is that when you go through this process, your inverse will also be a function. You don't have to worry about like plus or minuses or dealing with things like that. So should keep it pretty simple that way. And not every function is one-to-one, clearly, right? I mean, there's a graph right there of a function that's not one-to-one. Here's the graph of a function that's not one-to-one, right? Draw a horizontal line through this, it's going to hit it more than once. So the graph of this parabola obviously is a function, but the graph of its inverse is not. Because when you switch x and y and you're looking at the graph of a function and the graph of its inverse, they are reflected over the line y equals x. Right? A function and its inverse are reflections over the line y equals x. Y equals 1x plus 0. Goes through the origin with a slope of 1. Right? And if you have this kind of graph, look, that hits a horizontal line more than once, now you have this graph over here because it's a mirror image over that line. Now you've got this vertical line test that's obviously going to fail. Okay. So that's just a little bit of background on one-to-one functions. So you know what the test is saying when it says, given this one-to-one function, find the inverse. Really all you have to say is, oh good, what I'm about to find will also be a function. Okay. So you don't get crazy and find a whole bunch of weird stuff. Okay. So hopefully that makes sense. Does that make sense? Okay. All right. I'm going to share my screen one more time and give you a little practice with inverses. And then I will start to write down the answers. And once you are good, you can go. You are good to go. Okay. Here I am hiding my little stuff. And I'm keeping it simple. Right? I'm going to try to keep it nice and simple for you. I'm giving you some one-to-one functions. Okay. There they are, lines. Okay. Those lines, every function that's a line passes both the horizontal line test and the vertical line test, right? If my arm was a line and it's a function, so it's not this one, because that's not a function, but I've got this, right? Any line that has a slope to it, as long as that slope isn't 0, if the slope is 0, then switch x and y, now it's vertical, that would be a function, okay? But if you have a slope to it that's positive or negative, like these three right there, you should be good to go to find the inverse and feel really good that what you found is also a function. Okay? You don't have to know what one-to-one means right now, but it's right there in the words. I mean, one-to-one. For every one x, there's only one y. For every one y, there's only. Okay, so I'm gonna kind of angle this over this way a little bit, because there's the process. Here are my solutions. I will move this closer in a sec, but I wanted to make sure you can really see that. I didn't call it 1. What did I call it? 7, 8. Okay. A of x equals 2x plus 2. And I'm going to talk through it out loud, just so that anybody that wants to hear it and feel really good about it is in good shape. Okay, step 1, rewrite it as y equals. Okay, so y equals 2x plus 3. Yay, step 1 done. Step 2, switch x and y. Okay, x equals 2y plus 3. Perfect. Nice. There's the inverse. It's right there. It's just not isolated in the way that we would like. So I'm just going to get y by itself. I'll subtract 3 on both sides. And I will divide by 2 on both sides. Okay. So I get 1/2 x minus 3/2 equal to y. And I'm just going to use inverse function notation. A inverse of x equals that 1/2 x minus 3/2. Simple process, nothing crazy. Slide this over now. So I'm presenting anyway, so my screen is probably small when you look at this. And you can always pin whichever thing you'd like to look at, whether it's my screen or whether it's the board. We'll do those 2 more, and then we're out of here. Get a 4x minus 1. Might be up too high. It might be glary up there. Hopefully you're doing okay though. And you just look at the answer and you're getting it right. Now, x minus 3 divided by 2 is just fine here. Negative. A lot of different ways to write this one. X plus 1 over negative 4. Negative x plus 1 over 4. These are all great ways to write this. Something I would avoid, though, would really try to avoid fractions buried within fractions. Okay, dividing by 1/2, gross. Okay, multiply by 2, right? Multiply by this. And if you're good, I'm good. If you have no questions, I will send you on your way. You are all set. Just drop your name in the chat for attendance purposes, so that I know that you're here. And we should be good to go. If you have questions, let me know. Stick around. If not, thank you all for being here. Oh, the glare wasn't too bad. Good. I'm glad we could see that. Awesome. Questions, let me know. Otherwise, I will see you back here tomorrow. We will do one more day of this filling in the gap, and I will put some stuff on Canvas. I also hope to have tests graded for you today. That's my hope, because I'm going to work on those during the 3rd, maybe during lunch.
Thank you.
Did you get mine?
Did I get your
Did you get my name on the chat
thing? Yeah, thank you.
Good.
I appreciate it. Thanks, man.